Today we're diving into an essential topic that can make your models faster and more efficient: dimensionality reduction. Let's explore how this technique can simplify complex datasets. Dimensionality reduction is all about simplifying your dataset by reducing the number of features while retaining the most important information. It's especially useful when you're working with high-dimensional data that might otherwise overwhelm your model, enhancing both speed and performance. Principal Component Analysis, PCA, is a linear technique that reduces the dimensions of our data by preserving variance. It transforms the data into a new set of components ranked by their contribution to explaining the original dataset's variance. For instance, in a dataset with features like height, weight, and color intensity of fruits, PCA can combine height and weight into a single component that captures size, simplifying analysis while retaining key differences. In this example, we apply PCA to the famous iris dataset, which consists of 4 features. By reducing the data to just 2 dimensions, we can visualize and analyze the relationships between different species more easily. The explained variance ratio provides insight into how much of the original variance is retained in these 2 principal components, indicating the effectiveness of our dimensionality reduction. t-SNE is a nonlinear dimensionality reduction technique commonly used for visualizing high-dimensional data in 2D or 3D. Unlike PCA, it focuses on preserving the local structure of the data, making it ideal for visualization and understanding complex patterns. For instance, imagine you have a dataset of customers with various attributes like age, spending habits, and product preferences. While PCA might summarize these customers into broader categories, t-SNE can reveal more intricate groupings, allowing you to identify specific clusters of customers with similar shopping behaviors. This code snippet imports the t-SNE class from the Sclearn library and initializes it to reduce the dimensions of a dataset, such as the iris dataset, to 2 for visualization. The n components of 2 parameters specifies that we want 2 dimensions, while random state of 42 ensures reproducibility of results. The line x t-SNE applies t-SNA to the dataset X, fitting the model and transforming the data in one step. Finally, the code prints the shape of the transformed dataset, confirming that the number of samples remains the same but has been reduced to 2 dimensions, making it easier to visualize and analyze the data. LDA is a supervised technique for dimensionality reduction that maximizes the separation between classes. For example, in a medical dataset where patients are classified as having either a disease or not based on various health metrics, LDA can help highlight the differences between these 2 groups. By transforming the data, LDA makes it easier for classification algorithms to identify patterns and improve the accuracy of predictions. Here we apply LDA, reducing the dimensionality to 2 while focusing on maximizing the separation between the target classes in the iris dataset. LDA works best in classification problems where you need clearer distinctions between categories. In summary, PCA is an unsupervised technique that reduces dimensionality by projecting data onto axes that maximize variance. t-SNE is a non-linear method used for visualizing high-dimensional data, focusing on preserving local similarities to reveal clusters. Finally, LDA is a supervised method that enhances class separability by finding linear combinations of features that best differentiate between categories. Each of these techniques has its own strength depending on whether you're exploring variance, local patterns, or class distinctions. Up next, we'll dive into deep learning and neural networks, but I might take a short break to focus on my education and projects. When we continue, get ready for an exciting new chapter in machine learning.